Okay, let's start. Can you hear me well? Yes. Okay, perfect. So yesterday it was a little bit fast. We saw the optimization, the Bayesian optimization to deal with to tune calibrate hyperparameter. I put some link here if you want to have a go, and I told you this one, maybe we can open this video. So if I click on this link, you can see I really enjoyed this video. It's a bit long, but in fact I still a little bit I stole some slides from Javier Gonzalez. So you can he has also a different video, but he's very dedicated on Gaussian processes, and he really explained well why using Gaussian process for Bayesian optimization. So I recommend to watch this video if yesterday was as clear. So I hope you get a little bit some intuition yesterday for the optimization, Bayesian optimization. Um, is Can I ask one student to give me just in 1-2 sentences what is the meaning of Bayesian optimization? Yes, no? Somebody want to have a go? Okay. So I click on this tutorial. It's not because in R, but just to come back very quickly, just to summarize what we have. In this tutorial, think about we have our cost function look like this, and this depending of a set of hyperparameter, just to easy the understanding. We have this function which is unknown, and you can compute this function at any point, but it's very time consuming because you need to do your back propagation with the weight and so on and so on. And each time you have one value for the hyperparameter, you need to again do all this optimization process. So at each try for an hyperparameter or a set of hyperparameter, this function is very time demanding. Okay, so I'll check using the node point to choose the next point that's the highest probability of being the minimum. Yes, intuition is good. Minimum respect the uncertainty of the value of unknown function, and yes. Okay, yes. So I just in this tutorial use TensorFlow and it do so. If you do a gradient descent, the minimum is there, but by using the optimization process, the Bayesian optimization is based on the acquisition function, remember? So the acquisition function is a trade-off between two things, which is the exploitation and exploration. So if you go on this tutorial, the idea is to have a surrogate of the function, which is quite difficult to compute. So you have, for example, here 4 points, and using an estimation of this function f using Gaussian process, it gives you the posterior of this function given these 4 data points. So you have the mean in in the dash, and after you have also the uncertainty on this function. So based on this first estimation, we want to draw another point, and we calculate our utility function, which here is we decided to use the expedition improvement, and based on so this is use the probability of improvement, and you will choose another point. And it's this nice tutorial, you can see this, choose another point, and as soon you have chosen another point, your Gaussian process is updating, and so on and so on and so on. Okay, so this we have used the expected improvement yesterday. Or are the mean variance calculated from the point we have? In fact, for every point you have the Gaussian process. So you don't have they don't have a mean and a variance, because this is, you can see that the function at the point you observe, you don't have variability, because you know that this point is real. Okay, and you compute the true function at this point. Make sense? So you can see that at the point, I cannot show on the screen, but you see at the point you don't have any variability, because you don't have any uncertainty, because you know that this function coming at this point. Make sense, Jad? So you have the expected improvement on the left, and based on the expected improvement, which is calculated for all the data points, you decide the new point which has the maximum of the expected improvement. So you expect that the best point should be at the place of the expected improvement, and after you keep going and keep going and keep going, and you wait there. I hope it'll be clear, but I want to talk about something else today. In your project, you can decide to choose a paper on the Bayesian optimization for hyperparameter. To be nice. Okay, so we go back to the slides. So today, so we finish on this part. Plenty of stuff to see. Okay, so I think you need talk already what is the multitask learning. I'm not so sure. So the multitask learning is you use a network for solving multiple tasks. So in fact, in this picture, you can see that there's some share layer, but you use this share layer, but you want to have different tasks. So I think you have a link or an overview of the multitask. So the idea of doing this can be also like a regularization, because in fact now the share layer are not completely specific for one task, because it will try to go to task A, task B, task C. So it could also help to not overfit your data. So we give you some example. For example, so multi-task learning is a way of solving multiple learning tasks at the same time. And how to do this? In fact, now as you have different tasks to perform, you will have different loss function. For example, here in this, what was in my example, multitask learning is you have some image and you want to see if there are a car or not a car in the image, and also if there are pedestrian or no pedestrian. Okay, so you have two tasks. So the two tasks share the same neural network. But of course, you have a loss function for car no car and a loss function for pedestrian no pedestrian. Okay, so now you need to define a combination of this loss function to train your neural network. So your neural network will be not specific at just one task. Make sense? So there are plenty of examples in segmentation, object detection, and I see an overview of multitask learning. So when you see this, maybe there are links. So it's like some links everywhere in the slides. So if I'm looking at this, of course this one doesn't work. Okay, just one doesn't work. Sorry, I need to, the PDF doesn't work, this one. Okay, good try. Okay, let's go. Okay, so this was the multitask, but we more focus about Yoni talk about this. Last lecture I was there about transfer learning. So transfer learning is very, very useful because now you know that a neural network, a deep neural network, require a lot of training data to perform well. And sometimes you have a new task to do and you don't have a huge database, a huge training set, but you still want to do something with your data. So the idea is to use a previous neural network which has been trained to another kind of image or training data, and use this architecture to perform your task. So this is the main idea. So transfer learning reuse models that have been trained on a different task than the one you are interested in. So I come back on this example, but now you have just one task A, image optimization. You have this number of images, a lot, and you have output, which is some car, cat, and so on. So this is task A. So it's based on images, and it classifies some, is a multi-class problem, okay? Everybody got the task A? So when you do this task A, it has been trained, nice performance on your task A, but now you have some data and on cancer data on the skin, and you want to detect if skin cancer detection, but you have less images, 100 images. So the idea will be to use the previous architecture and the previous model, and of course you don't want to classify car, cat, because if you have some, you want to classify if the cancer is malignant or I don't remember how to pronounce this one. Okay, cancer or not cancer. So in fact, you can see, you take all the layers, you cut the last layer, the output layer, and you change by putting your task. And here is, before it was a multitask program, so it was a softmax, but now you put a sigmoid and you change it. So you train only the last layer, or you fine-tune the whole network. So the idea is that the low-level features learned from the task A are helpful for solving the task B. So keep in mind that transfer learning is not always applicable. It is applicable when task A and task B have same input, so here is image, and you use mostly this when you have more data in the task A than in the task B. So we'll go some different kind of transfer learning. You stop me if something is not clear. So with the nice pictures. So what is the main point on transfer learning? Pick up a model of the chef, adapt it to your target task. So, for example, you have a source of data which is ImageNet with a lot of data, and which is have been shown in experiment that is useful to use the model on ImageNet, and you transfer this on a smaller data set with your target data, and you change from your I'll say the output layer. Sorry. So what I'm saying is that at the end, the features from ImageNet are highly transferable. So this has been quite exploited in image recognition task. So how it's working, in fact, you can see this like you transfer your neural network, you cut. It's bad because I cannot. Okay, sorry, I will just change something. Yes, I prefer to take this one. Yes, sorry. Yeah, good. Now I have my pen. I prefer to talk with the pen. Okay. Yep. Okay, we are there. Do this? Yes. Okay. Okay. So you transfer your network. So here I cut here because we can see that you have seen with Yoni that in convolutional neural network, the first layer at the beginning, in fact, are quite general. There are some edge detection and is low level. So they manage the first layer to capture the main features of the image. And after, when you go deeper and deeper, the layer are more specific. So it's the reason what is working the transfer learning. So most of the time you take the first part of the network, you transfer, and after you adapt with your shallow classifier for your own task. But what is the meaning also is this weight here have already been estimated. So you don't have to do anything. And you just, in fact, optimize this part. And this one could be, we see, just fixed, or like a starting point, like a warm-up. So you have your initial value, which have been already trained before with another data set. And after is called the fine tune. So it's a meaning that you start your optimization at the starting point. I don't know if I was clear. So I just in this, so explain the fine tune. So, oh, okay, you see there, okay. And so you can see that in this example, so this is your source model. So the source model is meaning that you have the data and you have already learned. So you transfer, and in this part is just a copy. All of this part is a copy. And there is your new part. So the new part starts to 0. So you have some random initialization. And this, in fact, when you say fine tune, is the meaning that you start from the weight which I've been using here. Make sense? So I say it's like a warm start. Yes, yes, yes. Okay. So what I just said before, CNN tend to learn edge, texture, and pattern in the first layers. So keep in mind that. So the initial layers tend to capture generic features, while the later on will be more specific to the task at the end. So the idea is now closer you go to the output, the more specific features the layer trying to learn, such as object, part, and object. So this is the reason why it has been exploited for image. So the process is you can fine-tune or freeze. What is the meaning of freeze? Is the meaning of freeze is in example that the first part here, as it captures the main features, the global features, you don't need to start to again to adapt this weight. So this weight is fixed, so it's frozen. But when you started to be closest to your task, you want to, even this part has been transferred, you will fine tune. So it's the meaning that you start with the output, with the weight estimated, with the train data. Okay, I hope it was clear. I put a link here, which is a nice tutorial using Keras. I go there. And if you want to have a go, he explain you to do a transfer learning, a classical one. So an image net classifier. So in this tutorial, you can, they show you how to download a previous classifier based on some image. So for example, it was some kind of image here, and the classifier managed to say, oh, this, the position is a military uniform. And now to do a simple transfer learning for the new task, we take the same neural network and just applied on a new kind of image, and is clearly tried to, it was on the flowers images, but on the previous neural network, they just have this class, the daisy, the flower daisy. So of course, you can see that for some flower is not so good. You can see umbrella, vase, and so on, because we don't have this class on the previous neural network. So now, if you adapt to your classifier, so you cut the last part and you put your classifier. And now, if you put your classifier, So this, you have all this this new class, and you can see that you can now, before it was what it was, yes, now you can see that is tulip, sunflower, and so on. But this class was not in the first neural network, so it does make sense. And it show you how to export your model. So you have this link, you can go on this part, and also it could be also for your project a nice thing to do too. Okay. Something I want to give you some intuition is when I prepare this lecture, I found this article and it was quite nice. I was surprising about this. And is it 2015? So from these two colleagues. So we talk about unsupervised domain adaptation. I try to be clear, okay? So the idea there is that you want to label, to have a neural network for classification, but you don't have in your data some label data. So you are so it's the meaning that you are unsupervised domain adaptation. So you have your source domain and your so the source domain is you have some image and you have a classifier, and now you have some new image, but you cannot do the simple transfer because on this image you haven't done the work, you don't have the label of the image. Makes sense? So you have, I would say, X and Y for the first, for the source domain. So you have your source domain. So this is your first neural network, which have been trained with a lot of image and so on. So the input, output. And now you have a new, you have, oh my God, where is it? And now you have your target domain. So the task you want to do. And you have some input, Z, but you don't have the label on your training set. You got the idea? So yes, thanks, Jack. So in fact, you can see this here. So this is your neural network in green. And so this green part is like, you can see like a features extractor. So he managed to get the main features and all this, and he has been already trained for the source domain with the Y, which was quite nice. And you have your loss function, and this is a label predictor, okay, which work, all these parts work well, okay. And he add on the side, based after the features, the green part, another classifier in pink, and this classifier, in fact, classify the domain label. So the meaning is it, this is a binary classifier here, and it can tell you, is your image when you input arrive here, is come from the source domain or it come from the target domain. Okay? So this classifier tell you this. So this classifier is, you go through this, you are there, based on the features of your image, which you have some image which from the target domain or from the source domain. And this classifier tell you is come from the source domain, is come from the classifier domain. Is okay at this stage? Okay, the trick is now. Now is the trick. If you do a simple, you still keep like this, is the meaning that it will be this green part every time, is the meaning that it can tell you, oh, is the data, the image come from the source domain, the target domain. But we don't want this, because if you do this, is the meaning that as you don't have some label for the target domain, this part, the green part, will be specific for the source domain. So the idea of this is to reverse, you can see here, reverse classifier. The idea, the intuition is instead to minimize this log function, we will maximize the log function. So is meaning that we try to have a bad classifier for the domain label. Why we want to have a bad classifier for the domain label is the meaning that now the green part, this green part will be not specific from your image data from the source or from the target domain. So in fact, we confuse the image. And the idea is that you have some image which don't come from the same distribution. So we want that all the data come from the same distribution. So is the meaning that after the green part, man is able to still be good to classify some label, but he will not be able to differentiate between the source and the domain. So the idea, instead to have the loss function here, we take the minus of the loss function. So instead to minimize, to maximize. Did you get the idea? To confuse the green part to be not specific to a kind of data. And after, you can, in fact, label your data which we haven't trained your neural network. We have trained a neural network on unlabeled data for the target domain. I was thinking it was cool, but maybe I didn't manage to tell you, to show you what is cool. Ah, thanks, Matt. So you get it, eh? Maybe I have some slides which is, okay. It's good because the explanation was after. So it's good, it's a summary. Each time I start to speak. So, three component, features extractor. Component exploited, it will learn to perform the transformation on the source and the target distribution. Source and target, we try to confuse. Label classifier will learn to perform classification on the transform source distribution. Since the source domain is labeled, the source domain is labeled, the target domain is not labeled. And the label domain classifier, which is to predict whether the output is the features from the source or the target. And as I tell you, the pink part is to confuse the feature extractor. So the green part is to confuse the feature extractor in order to create features that allow the domain classifier to work well, but it still can create features that allow the label classifier to perform well. Okay. details in the original paper here. So if you click here, you have the nice paper, what I want to show you, this nice paper. It could be also a nice paper for your project. And it gives you some, oh, this picture is there. And it gives some experiment on this kind of data. So you have the means data, which you know it's the means data in the black clear, and you have the missed M, which is you have some digit with a different background, and these digits have been created by doing some difference between two digits. So this is quite nice, also nice data to play with is NIST M. So here is your source domain, which is a means data, and your target domain is this is a means M, but you haven't labeled them. It's still some digits to label, but you can see that the data are not the same distribution. It's some figures, but not the same distribution, is because you have different background, and it's also been built by doing some difference. And they give you some result by performing this neural network. All good? You get the data? Kind of data which are same kind of data, but not the same distribution. Okay. I would like to have some people who talk. Okay. Data augmentation. What is data augmentation? You know that the deep learning requires a lot of data, but sometimes you don't have enough data, or you have some data, but you want to be more generalized, not overfit, so you want to expand your database. So the idea is to collect more data, to have more variability in your data, and so you overcome the overfitting issue. Okay, so always good to have more data. So you can collect some data. If you cannot collect some data, you will transform the data you have. So it's called the image augmentation. So the image augmentation is quite well known for doing some simple transformation like flipping, rotation, translation, cropping, and so on and so on and so on. So you have an example there, I some code to do all this transformation, flipping, rotation, translation, and so on. And here I tell you, I ask Yoni, my best friend, to put you this link on the, I don't know if you put this link. If you click here, I think, here, on these twins, they did a nice job. We did some, oh, no there, yes, oh no, I got, yes. We did some sheets. So for example, is this one, which is quite nice. For the convolutional network, I give this to the student yesterday in our prac. And you can have the explanation of the different layer and the convolution and the poles, and it's quite nice also for your for your quiz 2. It gives you what's the meaning of the padding and the dimension, and or to understand the dimension when you do convolutional layer, max pooling, and so on and so on. But what I wanted to show you is for the object detection. So the data augmentation. Where is my data augmentation? Data augmentation. So you have this link, which is quite cool also. I just wanted to show you some or to do some data augmentation. So you have your image and you have different way to do some data augmentation. Okay, but you can also do some data so it has been used for image classification, objectation, but be careful when you do, for example, something just to tell you that if you do some flip, and it depends your data, because if you flip a B and a D, it will not change nothing. You will change your label. Okay, so be careful. And you will see on 7 that another way to do data augmentation is also to use a neural network. So like the GAN, you can see that we can, after chapter 7, you will see that the GAN can produce also some image for doing data augmentation. So you have a recent survey of image data augmentation here. So a survey of an image data augmentation for deep learning, 2019. Okay. Okay, so this was data augmentation for image, but we haven't talked too much on this lecture. In this exam, the book, what if the random crop focus more on the book, therefore changing the correct label? Yes, this will be not so good. Yes, the data augmentation is controlled by the user. Good point. Yeah. We haven't talked about too much about neural network for natural language processing, and we will have some example with me in chapter 8 when we use recurrent neural network. So natural language processing is a huge field, and the main task of natural language processing is, for example, I will say machine translation. You speak in English and you want to write in English and you want up the translation in French. Or you write in French, you want the translation in English or any language. So this is when you write on Google Translate is a neural network behind. We will not have completely a unit on this, but we will, because you can spend 30 hours on NLP. But I will just give you some insight on lecture next week on recurrent neural network. I will try to get an example on this, okay? So also in natural language processing, we can do also some data augmentation. So like a synonym replacement, random insertion, random swap, random deletion. So you, like another task, I saw this is an application, an apps, which is called Sign All. I need to find out, which is this application is convert the scene language to text. So this is a very nice application on natural language specific. So if you want to dialogue with somebody you cannot talk and you don't know the scene language, you have the scene language and up give you the text. So it's quite good. I put a link here also for the different example. Already 10, 15. Oh my God. So what can I say? Information. I will talk about BERT maybe which is one big neural network in the NLP, and it was in 2018. It was using for machine translation, and it was using developing by Google. Okay, I will maybe finish by this part. Just really quickly to see what is going on after. Or I can come back on this one. Okay. Yes, I will take five more minutes, okay? Okay, because this example is quite nice. Choose a good metric. I come back with the example with the skin cancer. So in this example, you can see in my slide, I have two models, model A, model B, okay? And I have the precision and the recall. Remember what is the precision and the recall, I hope? So if I'm doing my two table, tick very quickly, click. So I have the prediction here, prediction. Tell me if it's not good. Prediction. Here I have the true, and here is negative, positive, negative, positive. So true negative, false positive, true positive, false negative. Did I mistake? Very quickly. Somebody can tell me what is the precision? What is the definition of the precision? No. So the precision, you focus on this part. Is it? So the precision is equal, precision is equal to, what is equal? Okay. What is equal to the precision? Yes. Two positive, so two positive, positive. Yes, perfect. Yeah, thanks, Jad. So it's this part, okay? But when you're looking at the recall, what is focus? Is focus on this part. Is it? So the precision is among the detected positive, and the recall is among the positive. Yeah. Makes sense? So it doesn't give you the same insight. So you have two models. The model A is better in precision than the model B, but the model B is better than the model A. So I just wanted to highlight one point, and the F1 score is an average of the two. So what is a good evaluation? Which model you want to use? So it's really depend on your problem, what you want. And if I change the metric, if I calculate the classification accuracy, for example, the model A is 5%, the model B is 8%. So it looks like the model A seems better. But in fact, you prefer the model B. Why we prefer the model B? Because the model B, it was better for the recall. And you are better on malignant melanoma tumor. So this, because your focus is on malignant melanoma tumor. So even if in classification error is better and precision, you still prefer the model A. So what to do is keep in mind that you can change your metric. So this is one way to deal with this. So you put more weight, or if on your metric. So your metric is normally you count the number of time when your prediction is different of the current, okay? But if you are more interested by not doing some wrong when you have malignant, because when you have malignant, you want to detect this malignant, okay? You don't want to miss some case. You can put more weight on a weight for when is malignant. Make sense? And so this on the package, you can change your metric by doing this. Or another way is doing some augmentation is to add more data set with malignant example. Just to surrepresent. You get it? So if you are changing the evaluation metric, you also want to change your cost function. And so that now your neural network will try to minimize this cost function. So the cost function is, in fact, you add a weight for the case or categories you want to be to do less error. So this was what one key point I wanted to tell you. And you can also be faced at another tricky stuff is when you have unbalanced case. So unbalanced case arrive in multiple areas, for example, in medical diagnosis, in fraud detection, and many area of you have a classifier to do, but you have one class which is underrepresenting. So you can see that you have your original data is like this. You have one class categories, we have a lot of data, and one is very small. So keep in mind that if you're doing nothing, is your model will be not good. You will think the accuracy is good, but the accuracy, for example, if I have two classic problem, you have 0, 1, and you have, for example, I don't know, 90% of 1 and 10% of 0. Of course, I can construct a classifier with an accuracy of 0.9, because each time I have a new data, I will say 1, 1, 1, 1. Make sense? So be careful when you have unbalanced case problem in machine learning or in deep learning. So you need to do something. So to do something, you can use resampling approach. The resampling approach is to do some oversampling or undersampling. So in this first case is to do some undersampling. So is a meaning that the majority of the class, what you do, you remove some sample from the majority of class. So this is undersampling. So after you have something equal. So it's quite bad because you lose a lot of information, you lose a lot of power. Or you can do some oversampling. So the minority, you replicate the data. But it's also some trouble. Yes, you need to do both. Because after you have some trouble also. No, not the test, for the validation. So the test data, you don't need to. Okay, let me think about this, John. For the test data, if you're doing no, it should be a white for the test data if you compare after. But for the validation, yes, you should do it. Or you have some hybrid approach, which is combine the both. And there are some other technique, which is to create some synthetic data from your data. So I just very quickly, 1 minute, is you can see that is just an example. You have the green and the pink, and you have the minority of class is this one. So you want to create new data, and the idea is just to build to take the neighbor and to do some a model, and to finally you create this data, which is a KNN model. So you have a new data here. So it creates some synthetic data, but this doesn't work for image data. So this is the main, the popular one is the SMOT approach. Okay. Or if you have unbalanced class, the way to go is to do data augmentation. So create new data, but not replicate completely, change your data, and on the minority class, or changing the performance metric. So is the meaning if you have unbalanced class, what I showed you before, in the same thing that you wanted to put more weight for the malignant, you can do some change your metric to tell to your network that there's some class which is in minority. 1 hour, 6 o'clock Friday. So I hope today my goal is, or after this weekend, after your nice quiz that you will find, that you try to put some sentence on all of these points, and just to think, you read this, say, okay, what is validation data, multitask learning, transfer learning, Bayesian optimization? Can I understand all of this concept? Sorry, I'm done. I don't say anything. I reply to a question now. Can I see some people? I was on the rush both my 2 lectures. I don't know. I hope you get some stuff. And if you want, I can come back to something specifically. You just send a message and Canvas, say, oh, maybe can you just please explain a bit more of this point on this point for the next week, because just 1 more week. Okay, nice weekend, bon weekend. Work hard, work with fun. Enjoy learning, enjoy deep learning. Have a nice weekend. In Sydney is a wet weekend. Ten, 7, still 7 people. 4. Bye, Jad. Bye, Jufan. Still there, Jufan. Have a good weekend. Yoni is for you.